Hello guys, today we are going to have a chemistry online tutorial. In this session we'll be focusing more on the industrial processes like the Haber process, the conduct process and the Ostwald process. These are the key topics in your O-level chemistry and they oftenly came up in your exams. So be ready guys to learn, to take notes and also remember to ask questions, right? So let us dive into the question. So we'll be using the November 2019 paper, O-level Zimsec paper, right? That's the paper which we're going to use for the session. And also remember that in our previous sessions we did these questions. So if you were not present in the session, you can go and check on our playlist on YouTube, right? So we are on number 6, right? So number 6 says we are given this table, right, and it is incomplete, showing the raw materials used in the production of nitric acid. So the production of nitric acid is what we call the Ostwald process, right? So it is the Ostwald process, right? So we are required to complete this table, providing the raw materials and then the source of the raw materials, right? So Ostwald process is defined as the catalytic oxidation state of ammonia. So it is the catalytic, meaning it is done in the presence of a catalyst. Oxidation of ammonia, so this is ammonia plus oxygen for the oxidation process. So the source of ammonia, the raw material, we've got ammonia and then oxygen, right? So the source of ammonia, it is the Haber process. This from the Haber process, right? So it is the Haber process. And also the source of oxygen from the fractional distillation of air, right? It is from fractional distillation of air. And we want to say, as I've alluded to before in my previous series, that for industrial processes they are governed by what we call the Le-Chatelier principle. So the Le-Chatelier principle states that if a system at equilibrium is disturbed, it will adjust itself to oppose the change and try to restore a new equilibrium. So that's the Le. So you should know the Le-Chatelier's principle, right? You should know the Le-Chatelier's principle. If a system at equilibrium is disturbed, the equilibrium will shift or will adjust it to itself to oppose the change and try to reverse it. So the industrial processes are reversible reactions, meaning to say they go or they proceed in either direction. So we want to maximize yield. So that's the main purpose of industrial processes, to maximize yield, to increase the rate of reaction, and also to minimize cost, right? So for our conditions, we need to use the conditions which will facilitate these 3 factors: increasing yield, increasing the rate of reaction, and also minimizing cost, right? So the reaction which occurs for the Ostwald process. So here we expand our session by including any other frequently examined topics which are related to these topics, right? So it is the catalytic oxidation of ammonia to form nitrogen oxide plus water, right? So to balance this equation, we put a 4 here, right? And also a 4 here, and also 6 here, and then 5. So this reaction proceeds in either direction, meaning to say it is a reversible reaction. So this is the forward reaction, and then this is the backward reaction. So this is the reversible sign, right? So we want to put the conditions. So So this is an exothermic reaction, meaning to say the NH of the products is less than the NH of the reactants, meaning to say some of the NH is being lost to the environment, right? So for the conditions for this equation to favor the forward reaction according to Le Chatelier's principle, we must decrease temperature, right? So to decrease, we must use lower temperatures. Why? Because according to Le Chatelier's principle, the equilibrium position will favor the forward reaction in trying to increase temperature. So if we use lower temperatures, the reaction will be slower. Why? Because according to the kinetic theory of matter, temperature is directly proportional to the rate of the reaction, right? So when we reduce the temperature, the rate of reaction becomes slower, meaning to say we haven't met the requirements, right? So we said for industrial processes, we're mainly concerned by the speed, the time, the yield, and to minimize the cost, right? So we want to use conditions which will facilitate the forward reaction at a faster rate. So we use a moderate temperature of about 700 to 900 degrees Celsius, right? And here we've got liquid, and then here gas, and then here gas, and then here gas. So increasing the pressure will favor the forward reaction. Why? Because the equilibrium position will shift where there are fewer number of moles in trying to increase pressure, right? So if we increase pressure, we are going to favor the forward reaction according to Le Chatelier's principle. But we use a compromised pressure of about 4 to 10 atmospheres, right? Why? Because it is very expensive to maintain higher pressures, right? So we're going to use a catalyst. So a catalyst is one which increases the rate of a reaction by lowering activation energy, or by providing an alternative route with lower activation energy. Activation energy being the minimum amount of energy required to start a chemical reaction, right? So we are going to use a catalyst which is platinum rhodium, right? So this is the catalyst for the Ostwald process, right? So this is the main equation, right? You need to know for the Ostwald process. And then the overview of the Ostwald process, we can say stage one, right? There is air is passed through the filter to remove the dust particles, right? Passed through filter to remove dust, right? And then stage two, ammonia is from the harbor process is oxidized, right? So this is the main reaction of the Ostwald process, right? To produce nitrogen monoxide, right? So the equation for this reaction is ammonia 3 plus oxygen, a reversible sign here, and then plus water, right? Then gas, then here is a 4, then here is a 6, right? Then here is a 4, and then here 5, and then here 4, right? So this one gas, and then the condition 700 to 900 degrees, then 4 to 10 atm, and then platinum or rhodium catalyst, right? So this is the stage 2. And then we are now moving on to stage 3 of the reaction. So stage 3, it is the oxidation of nitrogen monoxide to give nitrogen dioxide, right? So it's NO plus O2 to give, so to balance this equation, a 2 here and then a 2 here, right? And then our stage 4, nitrogen dioxide is mixed. It is mixed with water and oxygen to form the dilute nitric acid, right? It's mixed with water and oxygen to give dilute nitric acid, right? So this is the equation, NO2 plus O2 plus H2O to give HNO3. 2 here, then 2 here, and then 2 here, right? So dilute nitric acid can be concentrated using the fractional distillation, right? So dilute nitric acid can be concentrated using fractional distillation, right? So you can also be examined on the uses of nitric acid, right? So it is one of the most frequently examined questions. Give us the uses of nitric acid. So nitric acid can be used to make fertilizers, can be used to make drugs, can be used to make dyes, can be used to make plastics, and also explosives, right? So this is the Ostwald process, right? And the conditions are here, and we are done, right, for the Ostwald process. So we are now moving on to the Haber process. So let me insert another page. So for the Haber process, it is the production. This is the production of ammonia, right? Production of ammonia. So we have the raw materials. Being hydrogen gas and nitrogen gas. So hydrogen is from the electrolysis of water. Electrolysis of water. So you should know the electrolysis of water, what occurs at the cathode, what occurs at the anode. So if you haven't checked on our playlist, we have another video simplifying electrolysis, right? So we have electrolysis of copper 2 sulfate using copper electrodes, electrolysis of copper 2 sulfate using carbon electrodes, and also the electrolysis of brine, electrolysis of molten salts like lead 2 bromide, and also etc., right? So you need to check on our playlist so that you can be notified whenever we post, right? So nitrogen is from the fractional distillation of liquefied air, right? Fractional distillation of liquefied air, right? So these are the raw materials and also the conditions. So this one it is also an exothermic reaction, right? So the equation for the Haber process, nitrogen plus hydrogen to give, it is a reversible reaction to give ammonia, and the enthalpy change being negative, right? So we have 2 here and then 3 here, right? So this is the equation for the Haber process. So for the conditions, we have a pressure, a temperature of about 450 degrees Celsius to 500 degrees Celsius, which is a moderate temperature. So this equation shows that the reaction is exothermic. Why? Because this is a negative enthalpy change. So the energy is being lost to the environment in the surroundings. So to increase the forward reaction, we must use a lower temperature. But using a lower temperature will cause the reaction to occur at a slower rate. So we want to increase the speed of a reaction at the same time maximizing the yield. So we use a moderate temperature, right, of this range. And also we are going to use a pressure. So pressure of about 200 to 300 atms, right? So increasing pressure will favor the side where there are fewer number of moles of gases. So this is in gaseous phase, and then this one gaseous phase, and then this one also in gaseous phase. So increasing pressure will increase the forward reaction, because we have 2 moles of gas. Here we've got 3 plus 1 to make it 4. So we've got 2 here and then 4 here. So increasing pressure will favor this forward reaction according to, say, Le-Chatelier principle. So you should know the Le-Chatelier principle by heart, right? So, and also you should be able to explain how the constraints affect the rate of a reaction, right? And then we are going to use a catalyst, ion as a catalyst, right? So it's powdered ion. So a question arises which says, why is the ion powdered, right? So according to the kinetic theory of matter, ion, to powder this ion, we are increasing the surface area, right? So this is catalysis, heterogeneous catalysis, right, where the catalyst and the reactants are in different phases. So ion is in solid state, and then the gases hydrogen and nitrogen are in the gaseous phase, meaning to say they are on different phases. So to powder this, we increase the surface area of adsorption of the hydrogen ions, the hydrogen and the nitrogen gases on this ion, right? So we want to increase the surface area by powdering the ion. So to use solid ion, it will catalyze the reaction, but at a slower rate. So to maximize the yield and also to increase the rate of the reaction, we use powdered ion, right, to increase the surface area for the adsorption of the nitrogen gas and the hydrogen gas, right? So these are the conditions of the Haber process. For the Haber process, we have a 15% yield, meaning to say a lot of the reactants is being recycled in the reaction chamber, right, to facilitate this forward reaction. So the two gases react in the ratio of 1:3, right? You should take note of this ratio, meaning to say 3 volumes of hydrogen gas reacts with 1 volume of the nitrogen gas. And also you need to remember the uses of ammonia. They can be examined in your exam, right? So ammonia can be used to make fertilizer, to make explosive, to make nitric acid, refrigerant, to make dyes, and also for water purification, and to make man-made fibers like nylon, right? So nylon, we can discuss nylon when we are doing polymerization, right? So we are now moving on to the conduct process. This is the last industrial process, conduct process, right? So conduct process, it is the manufacturing of sulfuric acid, right? So sulfuric acid. So the raw materials for the conduct process, we've got iron, we have got iron pyrites, right, with the chemical formula iron sulfide, right? And we also have sulfur, right? We can also have water, and then oxygen from air, right? And then concentrated sulfuric acid, right? It can be made in the lab, right? So this conduct process is done in 4 stages, right? So the first stage is to oxidize the sulfur containing compound. either sulfur or iron pyrites, right? So on the smaller plant, we can use this equation to say smaller, that's a smaller plant. We're having sulfur plus oxygen to give sulfur dioxide. And then for the bigger plant, we use iron to give oxygen plus oxygen to give iron 2 oxide plus sulfur dioxide. So to balance this equation, we are going to have 2 here, and then 2 here, and then 3, and then 2 here, right? So this is how we balance this equation. So we are trying to increase or to form sulfur dioxide, right? So that's the main purpose of these two equations. So this is the first stage, like the stage 1, right? So stage 1. So this is done in four stages, right? So the second stage number 2. So stage 2, there's the further oxidation of sulfur dioxide to give sulfur trioxide. So this is where the conduct process is, right? So this is the main reaction. So sulfur dioxide plus oxygen with a reversible sign to give sulfur trioxide, right? So we can put a 2 here and then a 2 here, right, to balance the equation. So the conditions of this reaction, we are going to use a temperature of about 450 degrees Celsius to 500 degrees Celsius, and then a pressure of 1 to 3 atm, and then vanadium 5 oxide or vanadium pentoxide, right? That's the catalyst for the reaction. And also remember that this is an exothermic reaction with a negative enthalpy change. So the conditions still lie within the same range, right? Why we use the moderate temperature, why we use high pressure, and also why we use the catalyst, right? So high pressures are difficult to maintain, that's why we use a moderate pressure here, and also high temperatures are expensive to maintain. So these are the conditions for the stage number 2, and we proceed to stage number 3. So stage number 3 is what we call the absorption stage, right? It is the absorption stage where the produced sulfur dioxide is being absorbed in the concentrated sulfuric acid to give what we call the oleum. So why is sulfur trioxide not added directly to water to give sulfuric acid? This is because it gives a film or a mist of sulfuric acid which are difficult to contain. So why do we? So that's the reason we avoid this reaction, right? Sulfur trioxide plus water to give sulfuric acid. So we avoid this this reaction, because it gives films of this sulfuric acid which are difficult to condense. So we absorb this sulfuric acid to already made this trioxide to already made sulfuric acid which is concentrated, right? So this gives us oleum H2S 2O7. This is what we call oleum, right? So oleum on stage number 4 is the dilution stage, right? So oleum is being diluted by water, right? So it's H2S2O7 plus water to give 2 moles of sulfuric acid. So you should take note of why we avoid this reaction, right? So that's one of the questions which can be examined in your examination, right? So we want to know the uses of sulfuric acid. Sulfuric acid can be used to make fertilizers, can also be used as an electrolyte in the car batteries, in electroplating, to make paint, to make detergents, also in paper making, as a drying agent, right? So these are some of the uses of sulfuric acid. So we are done with the industrial processes, and we want to go back to our question, right? So the question says, to the question paper, right? So we are done with this part, right? And we are done with this part again. So we are starting on number B. So which you are required to calculate the oxidation state of sulfur in hydrogen sulfide, right? So this one, the oxidation state of hydrogen is +1, and then this one X, they are known, so it's +1 by 2 atoms of hydrogen plus X, which is equal to 0. Since this is a neutral molecule, so it's 2 plus X is equal to 0. X is equal to -2. So the oxidation state of sulfur in hydrogen sulfide is equal to -2. And then for sulfur in sulfuric acid is H2SO4. So X, and then here -2, and then here, so here is +1, and then here is X. So it's X +1 multiplied by 2 plus X, and then -2 by 4, right? -2 by 4. So it's 2 by X, and then -8 is equal to 0. X is equal to 8 minus 2. X is equal to +6, right? So the oxidation state of sulfur in sulfuric acid is +6, and then here is -2. And then write the chemical formula of ammonium nitrate, then nitrate ion, right? So this is how you write a formula. So if you haven't checked on our playlist, again, we have a video which teaches how to write chemical formulas. So we have a fast and the easiest way to write chemical formulas. So now moving on to the next question. So the next question says, write the chemical formula of ammonium nitrate again. So it's ammonium and then the nitrate ion. And then name the 3 types of bonds in ammonium nitrate. So ammonium nitrate is made up of the ammonium ion and then the nitrate ion. So for the ammonium ion, we have this formula, right? Plus, meaning to say it is a radical or a polyvalent ion. It does not exist on its own, right? So we've got nitrogen being the central atom, and then hydrogen here, and then hydrogen here, and then hydrogen here, and also another hydrogen here. So it's hydrogen, 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 and then hydrogen. So the nitrogen is a period 2 element with the electron configuration 2, and then 5, and then hydrogen 1 electron, right? So nitrogen needs 3 electrons to attain the stable noble gas electronic configuration, and then hydrogen needs 1 electron to attain the Joublet state of helium, right? So 1 plus this one for nitrogen, and then 1 for hydrogen, plus this one for nitrogen, and then 1 for hydrogen, and then this one for hydrogen, right? So we've used 3 electrons from nitrogen, 1, 2, 3, and then we are left. So for the valence shell, you have 5 electrons, right? And then we have used 3, meaning to say we are left with 2 electrons. So 2 lone pair of electrons. So this positive sign shows that this proton doesn't have any electron, right, for the reaction. So this it is electron deficient. It counts to the reaction without an electron. So the lone pair or the unreacted 2 electrons from the nitrogen atom are used in the bonding with this hydrogen atom, right? So this is what we call dative bonding, where one atom donates all the electrons in the bond. So these 2 electrons are being donated by nitrogen alone, right? So this is what we call a covalent dative bond. So the displayed formula, we have, and then hydrogen here, and then hydrogen here, then hydrogen here, and then hydrogen here. So this arrow shows that electrons are being shared from nitrogen to hydrogen. So this shows that it is a dative bond. So we have covalent bonding, right? So sharing of electron, covalent bonding, and we also have dative bond. So dative bond, it is a type of covalent bond which is done by period two elements to avoid the expansion of the octet. So it is what we call the dative bonding. And then the other type of bond is what we call the ionic bonding, found between this ammonium ion and this nitrate ion. So ionic bonding is defined as the type of electrostatic force present on the oppositely charged ion, the cation and the anion. So that's the definition of the ionic bond. So for this question we are done.